All right. Let's go over the end of the review, the end of the year review. We're going to go over sections C, D, E, and F. If you do have any questions, just let me know. But I'm just going to pick a few problems until I see some questions about how to do it. So on part C, it's asking us to describe the transformations. Now, and I don't know how many viewers are. Like I said, the thing's all messed up, so I don't even know if people are watching or anything along those lines. So say hi in chat if we're here. But basically, the transformations we went over, that there were essentially, I guess you could say, 5 transformations. So let's kind of look at the generic function. There was a value in front, so to be a f of bx minus h plus k. Now, A, how's it going, Jocelyn? So A was our vertical stretch or shrink. B was our horizontal stretch or shrink. H was the horizontal shift. And K was our vertical shift. Now, I know I said that there's basically 5 transformations, while I only wrote 4 down. Depending on if A or B is positive and negative, we have reflections. So if A is negative, that's a reflection over the X. And then if B is negative, that's going to be a reflection over the Y. So there it is. You can always go back to it and reference it at a later time. But essentially, these are all the transformations that we can apply to our function. What's going on, Galena? So let's go over a few of these, and then if you guys need me to do a few of them, if you have any questions on, we can go ahead and take a look at it. So I'll start with number 6. Number 6 looks like there's a lot going on with that one. Okay, so we have f of 2x minus 2 and then plus 3. So, a few things to note. There is a formatting thing that kind of goes on when it comes to the horizontal stretching and shrinking here. Basically, we like to write it in such a fashion to where, and I know I didn't emphasize it when I wrote it out in the previous slide, but we actually like it like this. Now, technically, definition-wise, we don't write it like that, but we want to write it like that. It makes our, I guess, the way that we will process the transformation, it makes it a little easier. So basically, it just means that if we have a value here, which I recognize as my horizontal stretching or shrinking, we kind of have to like factor it within that little parentheses. So I actually want to rewrite this as f of 2x minus 1 plus 3. It just makes it much easier for me to categorize it, especially when we actually go to graph it itself, like if we are actually apply it. Having it in this form makes that application part much easier. So now that it's in that correct format, I can go and I can look at that and I can say, okay, so that 2, that's going to be a horizontal shrink. Factor of 2. Then because it says x minus 1, I know it's going to be a horizontal shift. And I could say positive 1. You could say to the right one, however you want to write that. And then because of this plus 3, it's going to be a vertical shift of up 3, positive 3, up 3 spaces. However you want to write that down. It's all basically the same. Now, a common source of confusion that comes along is going to be, we're so used to the fact that we have the vertical stretching or shrinking. We know that it's positive, we're getting a stretch. Or if it's greater than 1, we get a stretch. If it's between 0 and 1, we get this vertical shrinking going on. Why is it the opposite when it's horizontal? And the reason is because it's almost, instead of we plug it in and see what happens, it's what would have happened if I plugged it in. So let me give it an example here, and hopefully this makes sense. Let's just say I have an input, so an x value of 2. So, and let's just say that translates into, that's just what my x is, and I'm trying to get an input of 2. Well, what would my x be? It would be 2. Let me expand this out because it's about to get blocked. So if I wanted to, let's just say I still wanted the 2, but my input was now 2x. Well, what value would I have to plug in for x? In this instance, it would be a 1. Here, if I wanted the 2, I would plug in, if I plugged in 2 for x, it would give me 2. If I wanted a 2 and it was 2x, well, I would have to plug in 1. Well, what happened here to here is the 2 shrank down to a 1. And so that's, I mean, it's kind of a visual way to work around to kind of show that that's why this right here, this value 2, is going to be this this horizontal shrinking. It's kind of like the opposite of the stretch. If I had an input of, let's just say I wanted 2, but it said 1/2 x. Well, what would my x have to be to then make it 2? Well, I would have to plug in 4. So what would have happened from here to here is it grew, it stretched by a factor of 2. So it kind of has, that's why it has like that opposite effect, is it's like a what would x have to be to get you that same result. So it's like you imagine that the input is there and it's stagnant. Now how would the x change to give you that same input? And that's why it has that opposite effect. Versus with the y, to get a y value, that's what affects the vertical. The only way to figure out what the y value is by plugging in the x values. So plugging in the x values yields you the y. That's why it has that positive correlation. As you know, A increases, it stretches. As B decreases, or as A decreases, it shrinks. Versus horizontal, it has the opposite effect. It's because if you imagine, like I said, if this is the input that I want of 2, well, if it's 2x, well, what would my x have to then be? 1. So it has that opposite, or the reverse thinking. Any questions on number 6? Is there any of these that you would like me to go over for you to check? Probably like number 7. Here, I'll go over number 7 so you guys can maybe check it. Hopefully, I'll pause here for a second. I want you guys to kind of look at number 7. I want you guys to kind of like, at least in your head, and we'll get to that. Number 2 in part F. So number 2 in part F, it says the different methods of solving it. So you'd solve it by factoring. And I'm going to get to F. So that's going to be towards the end. I kind of want to keep it linear. And then the average rate of change is f of b minus f of a over b minus a. But I'll definitely do number 2 when we get to part F. Okay, so on number 7, negative 2f of negative 2x plus 2 minus 4. Okay, so I said we have to do the formatting. So I'm going to write that as negative 2f, factor out that negative 2, and so I'm going to get x minus 1 minus 4. So I'm not going to actually explicitly write them out. I'm just going to kind of talk about it as I go through it. So here, that negative is a reflection over the x-axis. So reflection over the x. Here, that 2 is a vertical stretch. Factor 2. The negative here is a reflection over the y. That 2 is a horizontal stretch, or sorry, shrink. Factor of 2. Then I have a horizontal shift of positive 1. And then I have a vertical shift, negative 4. So that pretty much covers every little bit from transformations. All right, so let's move on to part D. So part D, we have inequalities. Anytime we have an inequalities, doesn't matter what type of equation, whether it's linear or quadratic, or it's a polynomial, or it's sine or cosine or whatever, it could be any type. The first thing we always want to do is find the solutions. So we pretend it equals 0. Those solutions are where it crosses the x-axis or our boundary points. And then we need to find whether it's either above or below. So the positive regions or the negative regions or the true regions or the false regions, depending on what the inequality is. So, for example, on number 1, we have x squared plus 8x plus 15 is greater than or equal to 0. So we can factor that. That factors into x plus 5 and x plus 3. So I'm pretending that it's going to be an equation. So I get x equals negative 5 and negative 3. Now the reason why I want that is because I'm going to take those values and put them on a number line. So I have negative 5 and negative 3. My inequality tells me how it interacts with that number line. So do I include the solution or exclude those boundaries? In this case, because it says equal to, that means I include them. And now I just need to know, is it going to be true or false in each reason? So true or false, true or false, true or false. Now another way of thinking of true or false is this value here. It says values greater than 0. Values greater than 0 are positive values. So where is my graph positive? Or where is it above the x-axis, basically? And so if I can plug in values in between here to kind of figure that out. So if I plugged in negative 6, I get negative 1 times negative 3, because I'm plugging negative 6 in for x. Well, that's a positive. If I plugged in negative 4, I get positive 1 times negative 1. So that's a negative. And if I plugged in 0, I get a positive 5 times a positive 3. Well, that's positive. Well, we said we're looking for positive values. So the positive values represent my solution. Those are what are true. And so my answer is going to be negative infinity to negative 5 union from -3 to infinity. So comments or questions on part D? Now number 3 is cosine. So if I subtracted the cosine, I'm going to get 2 cosine squared x minus cosine x is less than or equal to 0. Okay, so less than or equal to 0, those are the negative values. If I factor out the cosine, I get 2 cosine x minus 1. So I have cosine x equals 0, and 2 cosine x minus 1 equals 0. If I do cosine inverse to both sides, I get x equals cosine inverse of 0. So where on my unit circle is my cosine going to be 0? And so that's going to be at pi halves and 3 pi halves. And the thing about this, though, there's no like boundary, right? I'm not saying only find the values between 0 and 2 pi. So technically, it's going to keep going and going. So if it's at pi halves and I go all the way around again, well, then that's going to be 5 pi halves. And then it's going to go down. So I get 7 pi halves. And then I get 9 pi halves. And then I get 11 pi halves. So it's going to keep going and going and going. Wow, that's messy. Now I have to do the same thing for, like, now the only reason why I did this is so that we can get kind of like a pattern. And I'll kind of show it out on Desmos, and it'll kind of help a little bit too. So the next, add the 1. So I have 2 cosine x equals 1, divide by 2. Cosine inverse. So where is my cosine going to be pi halves? Now in the unit circle, that's here and here. So that's pi thirds and 1, 2, 3, 4, 5 pi thirds. So that's going to be pi thirds and 5 pi thirds. So now I have to consider those keep going as well. So we have like 7 pi thirds and 11 pi thirds. And that's going to keep going on and on and on and on as well. So on my number line, here I'm going to make this larger. On my number line, we're going to have pi thirds, and then we're going to have pi halves, and then 3 pi halves, and then 5 pi thirds, and then 7 pi thirds, and then 5 pi halves, and then 7 pi halves, and then 11 pi thirds. So basically all I'm doing is just writing these in order. So this was first, so a third, then a half, then 3 halves, then 5 thirds, then it was 7 pi thirds, and then 5 pi halves, and then 7 pi halves, and then 11 pi thirds. So you just write them all out in order. They're all closed circle. And now we have to test true or false on every single one of these. Now, the only reason why I'm writing it out like as almost I'm doing it infinitely is because I'm just trying to find a pattern. So let me kind of show you in Desmos how that's going to look. So it's going to be just a tad bit easier. So 2 cosine x, or cosine squared x minus cosine x. Okay. Now I'm going to switch this over to radians. Oh, it already is. Good. The other thing that I think I'm going to do is I'm going to make everything along the x-axis, every step, I'm going to make it a pi 6. Where's pi? Pi 6. There we go. So that's just going to be a little easier so we can see there's our pi thirds, there's our pi halves, etc., etc. So because it does say values that are less than 0, values that are less than 0 are negative, that's where it's below the x-axis. So between pi thirds and pi halves, that's going to be true. So this right here is shaded. Here, maybe I can adjust this so I can have both at the same time. And then it looks like between 3 pi halves and 5 pi thirds, that's also going to be shaded. And then it looks like between 7 pi thirds and 5 pi halves, it's also shaded. Now, like I said, all we're doing is just establishing a pattern. So between 7 pi halves and 11 pi halves, it's shaded. Once you establish a pattern, all you got to do is just do dot, dot, dots. So I could say my interval notation is 5 pi thirds to pi halves, union, 3 pi halves to 5 pi thirds. I can do dot, dot, dot on this side. Let me see if I can get more room. No. I'm going to write a little smaller. Union, and then 7 pi thirds to 5 pi halves. And then dot, dot, dot. So I've established a pattern now. Now that the pattern's established, we're good. I'm basically saying if I take this statement and I follow it this way to infinity and that way to infinity, it's going to represent every single possible value. This is a crazy one. It's a long one. Are there any questions on that? So I know I went a little bit on the quicker side on it, mainly just because instead of just spending all the time plugging it in, seeing if it's true or false, we can just look at Desmos, where is it below the x-axis? And I found all the areas in which it's below it, and that's what our solution represents. Okay, great. Any of the other ones in this section? Are there any other ones in this section that you guys would like me to go over? Okay, Well, let's go over part E. Now, like I said, if you guys run across into anything as you go through it yourself, ask me in Discord. No worries. Just make sure you mention it, because sometimes it won't let me know if you just post. And so just if you @mention it, then it sends me a notification. All right, so part E, factoring completely. So there's just different types of factoring, and we just need to go through and figure out how to factor it. So for example, for number 1, I would look at it and be like, oh, there's only an x in common, so I'd factor out an x. There's nothing else we can do to factor it. For number 2, between 3 and 42 and 15, okay, so maybe a 3's in common. There's not an x in common with everything. There's not a y in common with anything. So I wouldn't factor out the x or y. On number 3, it seems like the only thing that's in common is an x squared. So this is kind of weird. But I have x squared minus 4 squared, and then I have x plus 2 squared minus, and then I have x squared minus 9 squared, and then x plus 2 squared. So it looks like I have an x squared in common. So if I factor that out, I'm going to get x plus 2 squared times, and then I'm going to get x minus 4 squared minus x minus 9 squared. I don't see anything else that could factor. And factoring just means to write as multiplication. So, boop. Let's look at, let's see, check for GCF, check for GCF. The 125 plus 27x cubed, that's maybe a sums and difference of cubes. First times first is first, last times last is last. So you may have to go through and look at that one. For number 11, so number 11 is a little tricky. So we have 12a squared b minus 42a squared minus 4b plus 14. So this one's tricky because you have to do a factoring within a factoring. So this might actually factor first. Actually, let me look at it. Actually, there's... we can actually factor out a 2 first. So I get 6a squared b minus 42a squared minus, whoops, (21a squared minus 2b plus 7. I'm just saying if there's something that I could factor out. Maybe not. Maybe that is it. Or, let's try this. What if, because I have 4 terms here, what if I try factor by grouping? So I kind of split the two terms. So this is a way that we can factor. And I look at what's in common. So there's an a squared in both of these. And then between 12 and 42, there's a 6. So then I'm left with 2b and then minus 7. And then over here, between a negative 4 and 14, I get negative 2. And so you get 2b minus 7. And so since these are the same, I get 6a squared minus 2. And I get 2b minus 7. There we go. So we had to do factor by grouping. So it's literally just, we got to have all these different types of factorings, and we just go through them. Do. And that's kind of like what I was just doing. I was like, oh, maybe this, no. Maybe that, no. Maybe this, no. You just got to go through them. Are there any questions on part E? Okay. Now let's try F. Okay, so their quest was part 2 in F. So part 2 in F, or number 2 in F, so I get plus 8x plus 16 equals 0. So it's asking us to solve, so it's quadratic. We could use the quadratic equation. That is one way. We could try and factor it. Let's see if it does. So 4 times 4 is 16. 4x is 8x. X times x is x squared. Yep. So we get x equals negative 4. So there's our solution. That's the first piece to this. Then it says, find the average rate of change. So the formula for the average rate of change is f of b minus f of a over b minus a. So it's giving us what our a and what our b is. So my a in this instance is negative 2 because it says when x is negative 2. So that's my a. And then it says when x equals 3, and so that's going to be my b. So it's asking for f of 3 minus f of negative 2 over 3 minus negative 2. So what is my function with 3 plugged in? So you'd plug in 3. So 3 squared plus 8 times 3 plus 16 minus, then my function with negative 2 plugged in. So negative 2 squared plus 8 times negative 2 plus 16 all over 3 plus 2, because negative 2. And you just got to simplify that. Make sure you do everything in this parenthesis first, because you're going to distribute that negative. So this was number 2 on part F. So you only have to do the average rate of change for problems 1, 2, and 3. We pretend it equals y. All right, any of the other ones for number F? Let's look at maybe number 9. So we have 10 over x times x minus 2 plus 4 over x equals 5 over x minus 2. So when we're solving rational equations, we need to make sure that the denominators are the same. Once the denominators are the same, it becomes irrelevant to what the solution is going to be. So that's going to be our first step. So this has an x, this has an x, this doesn't. So I need to do x over x. So now all three of them have x's. This has an x minus 2. This one doesn't. And this one has an x minus 2. So now the denominators are the same on everyone. So now we can, like I said, it's irrelevant, so we just kind of ignore it. So we get 10 plus distribute the 4. So 4x minus 8 equals 5x. Combine like terms. Minus 4x. I get 2 equals x. Now, because rational functions are one of those values that, or one of those types of functions that we may have domain restrictions, like we can't divide by 0, it means that when we solve, there could be things called extraneous solutions. So we have to plug the values back in and make sure that there's no extraneous solutions. Well, if I take this 2 and I plug it back in, I get 2 minus 2 in the denominator, which is 0. I'm dividing by 0. So that can't count as a solution. And so in this instance, it's going to be no solution. And that's how we solve rationals. All right, any other questions in part F? Okay. Well, if there are no more questions, then I'm just going to go ahead and end the stream here, which is okay. Please post in Discord your questions if you guys have questions on tomorrow's stream. I do have a meeting from 9 to 10 a.m. I'm hoping that it's done at 10. If it's not done by 10, I might be a little late, just depending on what happens. So just be aware of that, but it shouldn't be a problem. But tomorrow, we're going to go over G, H, and I. So we're going to go over G, H, and I. Well, all of those that participated, thank you very much. And I will see you guys tomorrow. Hope things have been well, and I hope you have a good day. See you, Jocelyn. Have a good one.